Okay, we were talking about forging and how you can forge out defects. I'm going to give you an example. Well, rolling, you're basically just squeezing the things like you're rolling out pizza dough or pie crust dough, and you squeeze the defects together. In fact, one type of steel that used to make in the old days being pre-1970, they had something called rim steel, where you actually developed the carbon boil, and you made Swiss cheese on purpose to get rid of this pipe shrinkage. And you could use the whole ingot, and then you rolled it into thin sheet metal and it all welded back together. The Swiss cheese holes all got rolled back together. That was called rim steel. The problem, and they also had cap steel. Cap steel, you could control the porosity size a little better if you put this kind of 2,000-pound cap on top of this boiling steel. The problem is you didn't want to be too close if they put the cap on too early, because sometimes it'd blow the hot cap off and you'd have molten steel fly all over for about 20 yards around. And people used to get killed in the steel mill for doing that, but not killed. I mean, they're not for doing it, but they got killed when it happened if they were too close to it. Hipping is a technology that was developed at Battelle Memorial Institute, although the second one was actually in a corner of what's now my lab back around the 1950. Right after World War II, to basically build a very large or very strong pressure vessel, has a screwed-in base and a screwed-in top, and I'll give you some dimensions of this in a second, and you put your part inside here, which is a gas part, and you put argon in here, and you go to about 2,000 atmospheres of pressure, which is 30,000 psi, and you can go to 1,500 degrees Fahrenheit. I have a little one of these that has a 4-inch diameter by 7-inch chamber in the lab, which costs about $100,000 for that unit. And it goes to 2,000 atmospheres and 2,000 degrees centigrade because it has a graphite furnace. So it can go to very high temperatures. 2,000 atmospheres for a gas, it has about the same density as a liquid. It's gaseous, but it has about the same density. And so basically, if I have a casting in here with pores and I heat it up to these temperatures where the metal becomes softer, I basically just squeeze the porosity out of it. And so I can basically take a powder metallurgy part and put it inside a can and weld up the can to keep the argon out, because I can't have gas in between the pores or I'll just trap gas in the pores. And I put it in a hot isostatic press for a 10-hour cycle and take it out, and I've got a solid part. Well, it turns out the advantage of this is you don't have a lot of shape change. In forging, you have a lot of shape change. In rolling, you have even more shape change as you're deforming the material. Here, you're not deforming the material, you're just squeezing it. Hipping stands for hot isostatic pressing. So you're doing it at temperature. It's isostatic because you have pressure, equal pressure from all directions, whereas in rolling, you're squeezing, and forging, you're squeezing from one direction. Here it's isostatic. It's just like putting it at the bottom of the ocean, right? You're squeezing it from all directions while it's hot, and you can squeeze out the defects. So typically now, we may cast in a near net shape a titanium turbine disc for an aircraft, and then take it over to the hip unit. You go up here to North Andover, Massachusetts, where they have one of the world's largest hipping presses at a company called IMT. It's the predecessor of IMT 30 years ago was actually a spin-off from some of the people here at MIT, but basically they have a press where the chamber weighs about 300 tons. Okay, it's about 200 tons for this and about 50 tons for each of the end caps. And the chamber is 64 inches in diameter. And the height is, I don't remember, about 8 or 10 feet tall. Okay. A typical cycle in this thing takes 24 hours. And one of these, about 3 or 4 years ago, blew up. Actually, it was the world's largest. They had one that was 60 inches at that time, and they had a new one on order for 64 inches. that fortunately, it takes about 3 years to build one of these things. Fortunately, the 64-inch one was coming on stream 3 months later when this one blew, the 60-inch one blew. And that's a good thing, because otherwise, construction of all large jet engines in this country would have been halted. I mean, it got delayed for 3 months, but I mean, it takes a few years to build a jet engine anyway, so it wasn't that big a deal, because that was the world's largest one. There now are 2 of these 64-inch ones, but the wall thickness of this thing was just under 11 inches. It actually had a shape like this. It's actually a little bit bigger at the top and bottom. It was 17 inches thick down here. They all forged pressure vessel to take those types of pressures, and they have a furnace inside. And someday, if you want, I can tell you some of the reasons off the videotape of why it failed. There are a multitude of reasons that have to do with fracture toughness, have to do with inspection looking for flaws, have to do with corrosion problems. But anyway, because the whole thing, at one point they decided to water cool the outside, and they got some corrosion. Anyway, those are some of the things that happened. So that's hot isostatic pressing. You have to have a fairly high value added part. It turns out Harley-Davidson, the jug for Harley-Davidson, or from a lot of your aircraft engine things that are air-cooled engines, you know, this is the aluminum finned cylinder. They call it a jug because the piston runs up and down inside this thing. Those are cast components that are then hipped to get rid of the defects. Okay, so you're getting rid of the casting defects. You're talking about $1,000 an hour for operation of that unit. So you're talking, you have to have enough value added to pay $24,000 for the load, at $1,000 an hour and 24 hours for the cycle. So you don't do this with parts for your Ford Explorer, but you do it with huge parts. And they have other size hipping units too, so far as that goes. So one of the problems with forging, it tends to be an expensive process. Rolling is cheap, but it only makes sheet or plate. And now I want to kind of give you a story, kind of a case study of, and some of these overheads are not the greatest. So let's see, we may want to bring down, if I can, some of the room lights. How do I get those lights off? At the door? Let's see. Okay, now you can go to sleep. This actually is a failure that occurred in October 1980. It was the LNG Libra. The liquid natural gas carriers, Libra and 5 of her sister ships were built down here in Quincy Shipyard, just a few miles away from us here. It's no longer a shipyard, but these were the big spherical aluminum tanks. They had 5 big spherical aluminum tanks. The tanks were big enough that the aluminum at the equator of the tank was something like 20 or 24 inches thick. And at the top, I think it was only about 8 or 10 inches thick. But these were big tanks. They were about 10 stories tall. And they held liquid natural gas. Well, it turns out that if you read some of these things, it says, this surveyor from the American Bureau of Shipping, at the request of the owner's representative, attended the Libra of Wilmington, Delaware. That's where it was registered, and gives ID. What's this? Gross tons. Says that's 83,700. So 84,000 gross tons. This is a fair-sized ship. As she lay off anchor of Davao City, Philippines on the 9th day of October 1980, and subsequent date, she was steaming fully loaded from Indonesia up to Japan, because that's what most of these 6 ships were doing, was taking LNG from Indonesia to Japan. On the 3rd of October 1980, when they suddenly lost main propulsion power while in a loaded condition on voyage number 30 from Bontang, Indonesia to Tabota, Japan. The vessel was towed to Davao Gulf and anchored off Davao City, Mindanao. And cargo was transferred to another sister ship, the LNG Leo, which was a very exciting transfer. They had never had to do this type of transfer before. and they were flying in on Learjets, pieces of hose and tubing and stuff, because not everybody has, you know, big 6-inch or 8-inch hose for LNG just in the middle of the Philippines, you know. No movement of propeller tail shaft with turning gear was engaged. Propeller still fitted on shaft with a pilgrim nut and blah, blah, blah. So here's the surveyor's report. The next page of the surveyor's report basically says they towed it to the to Singapore, and that's his report on 12th of October, and it was supposed to be in there on the 13th of October, and this all occurred originally on the 3rd of October, and then I think it was about 3 days, and they were fortunate they didn't blow up the harbor, although harbors have been blown up by liquid natural gas explosions. There was one in I think it was Bahrain. It was somewhere in the Middle East where they were making liquid natural gas, and the British had a fracture toughness spec for and they made the liquid natural gas vessel, which is what, minus 200 degrees Fahrenheit or something. They made it out of carbon steel, welded carbon steel, and this met a British specification at the time. And there was a welding flaw, and they originally tested it in salt water. I mean, they wanted to do a hydro test on the vessel. LNG is not as heavy, so they only hydro tested 60. They only filled it up 60% of the way through. I mean, this was just kind of a gravity hydro test. They didn't pressurize it. And since LNG is lighter than water, they only filled it up 60% of the way, which meant they actually didn't hydro test the welds on the top of the vessel. And it's just a big storage tank, right? And then when they filled it up with LNG, a few hours later, it blew up and wiped out the entire harbor. It turns out this whole thing, I wasn't involved in it. Professor Pellew, who's retired, actually was involved in it. It went to the World Court, and Royal Dutch Shell actually won against the government of Bahrain or whatever, because they had, the alternate theory was the Sheikh of Bahrain had a lot of enemies, and that this most likely was a bazooka attack. Okay, so there's the old sabotage alternate theory. Of course, after that, Royal Dutch Shell, apparently to this day, no longer does business in Bahrain because the Sheikh doesn't care much for them for blowing up their harbor. But anyway, that was a fracture toughness problem. So LNG will blow, and when people get worried about what could happen to Boston Harbor, well, maybe it'd be better off blown up, who knows. Dry docking survey, propeller shaft survey, further report, let's see. So they ended up in Singapore to examine this and see what happened. And the second page, isn't this great? 2-page reports, surveyor reports. Or maybe this is a 3-page report. Says the tail shaft was found sheared in 2 pieces, and the same was renewed at this time. Found satisfactory. Tail shaft was examined. That's the stampings on the tail shaft. So they identified what the forging was that had made this thing. And let's see what else they say. It had been ultrasonically inspected at the owner's request for forging, segregation, and piping. Well, you now know what piping is. And then they recommended the vessel be reclassified. Well, okay, so what actually happened? Well, here's a drawing of the tail shaft. Have a 33-inch diameter shaft. This was made from about a 20-ton ingot, forged from a 20-ton ingot. It turns out it was forged at a steel mill in the northwestern part of the United States, and then it was shipped to Quincy. They had to use their largest ingot mold to make this. In fact, they were sort of not, this was just at the limit, or maybe it was even just beyond the limit of their capacity to produce a part this size. But they wanted the business. They also forged the intermediate shafts, which were only 30 inches in diameter. The tail shaft was 33, and that's where it fractured, and that's why they lost power. So why did it fracture? Well, there's actually a number of stories here that kind of tie together a number of things we've talked about. You want to see a picture of the tail shaft. This is the forward end of the tail shaft, and here's the fracture. And a couple of interesting things about this. There's a man standing back here, so you get a little scale. Okay, see the man with his hard hat on? This is in the shipyard in Singapore. When they've taken it out, you have this hole right here in the center. Turns out that's not casting pipe directly. I'll show you what that is in a second. You have a rough fracture all around that, and then you have a smooth fracture all around this. and I'll explain that fracture in a second. Looking a little closer, this is when I went to Singapore to take a picture of it in the junkyard. They had cut out some samples, and there's a ruler sitting there. But you can see the rough fracture. You can see these lines. You can see the smooth fracture up here. Well, if you know how to read fractures, that tells you how the fracture grew. Here's another picture showing the hard hat sitting on top of the thing, and you can see this hole from the side here in the center of the thing. Well, let me show all those. So how did they make this thing? Well, here's actually a picture of a steel company book on how to make steel, not of this thing, but on heavy press forgings. And so here's a man standing there. This thing is at about 2,000 degrees Fahrenheit. So it gets hot. I remember the first time I ever went through a forging shop like that. Even when you're standing 20 feet away, there's a lot of radiant heat. I also remember when I went to a forging shop like that 27 years ago, first time. And these guys, this thing actually has to stay in the furnace for about a week to bring it up to temperature. It's so big to diffuse the heat all the way through. And now it's in the furnace, it's an air furnace, and you'll develop about an inch thick of oxide scale. It's just oxidizing in the furnace. And so when you forge it, the scale falls off. And that's the kind of, you see the black surfaces here? That's the oxide that's starting to flake off and stuff even before they hit it. And then the whiter areas are basically where the scales already come off and you're seeing the hot steel underneath. Anyway, so they forge this and all the scale breaks off. And while the crane's putting this back into the furnace, they had two guys with shovels that would go and shovel up the scale and throw it in a dumpster. Of course, this is a hot scale, probably at that point only about 1,000 degrees. And it was just amazing to me to see these two guys. While one of them would go down, the other one would be throwing it over his shoulder into the dumpster. And the other guy was closer to the dumpster. He didn't throw it over his, So the more experienced guy was the one. And they were just perfectly coordinated. One would go down and one would come up, just like a piston engine in two cylinders going up and down in perfect synchronization. And I said to the guy next to me, I said, what if they lost synchronization? He said, then one of them would get burned, but they won't because they've been doing it for 30 years. So, and that's what reminded me why I got an education. Here's these are on rail cars, so we railroad cars to carry them around. These are hot forgings, two different ingots. This actually is still the ingot mold. It has little flutes, and that's the hot top to try to reduce the porosity. This one is actually probably already been forged. The largest forgings in the world are 700-ton castings that end up producing a 350-ton generator rotor for one of these utility steam turbines that generates electricity. So if you have a 1,000 megawatt electrical turbine generator set, it will have a 350-ton steel forging. And those are made in the same plants. I told you before, there were only 2 plants in this country that could forge battleship gun barrels. They were built before World War I. That's what we use those facilities for today. And so when Bethlehem Steel shut down and went bankrupt, it turns out the only thing left at the Bethlehem plant is that forging facility to forge these old battleship gun barrels and now generator rotor forgings. It takes about a month to forge that 700-ton casting, okay? Because you got to put it in the furnace, bring it out and forge it, put it back in for a week, pick it up and forge it. Then, if you do that 4 times, it takes a month worth of forging. And then you got to have some pretty good sized lathes that not everybody has to turn these things. Not everybody's got a 100-foot bed with a 12-foot swing on your lathe, but they have these, okay? Okay, there's the forging porosity in our tail shaft, okay? Not forging porosity, that's the porosity from the original casting, so far as that goes. Because, like I said, this steel company really probably shouldn't have bid on this contract. They were really pushing the limit. They did not get a lot of squeeze into their forging, a lot of reduction. You typically would like to get at least 75% reduction to squeeze out the porosity, but they didn't. They really were pushing the limit. If you actually look at the cracks, and this is the microstructure, the grain structure of the steel, you actually see the porosity and you see the cracks running between the partially forged porosity. in these things. So if you then produce a fracture map of this thing, here's our big void in the center, and it turns out this rough area in here was actually another forging defect. This was a casting defect, which was produced, the hole in the center was a casting defect that was produced from the center pipe. And I got my thing out of order a little bit here, but somewhere in here, I've actually shown you this thing before. Get out. Where'd I put it? Let's see. Well, in any case, it was the casting pipe that we talked about before, but it was just below it. This was actually part of the casting pipe, but as the metal solidified at the bottom of that cusp of porosity, there was a pore right beside it, about the size of a football. Okay, that was the original flaw, and from that grew the during forging, because of stresses, thermal stresses during heat treatment, or when they put it in the furnace, they basically got what they call a clink defect. And the clink is caused by the fact that if you are not careful and you just try to put a hot piece of steel into a you didn't have to scan that in, did you? Anyway, we'll have to talk about that later, where that thing is. If you put a hot piece of steel into a furnace and the outside of that cylinder starts to heat up first, that goes into compression, and so the surface goes into compression and the center goes into tension. If I've got a defect there and the steel is cold, remember steel is more brittle at low temperatures. When I first put that in and I've got a defect right in the center and I put this into compression and this into tension, I've got a brittle material in tension, and I can have a brittle fracture that runs all the way through the tensile region until it hits the compressive region and it stops. And when it does that, it goes off like a gunshot, and they call it a clink. It's more than a clink. It's like a rifle shot going through the plant, and people should have heard it if there was anyone around, or if they knew what they were listening to, or if they weren't drunk, or whatever at the same time. And so this whole area in here was actually a fracture that existed when they shipped this thing from Seattle to Quincy, plus this defect here. The rest of this and these other lines on here, the crack grew out this way, and then fatigue cracks in operation grew this way in rotating bending. And remember I showed you the fatigue crack pattern. You can go back to that and you can prove to yourself. The final fracture was right up here. Okay, we call that 12 o'clock. And you can see all the arrows converging, and it finally, that was the final area of separation, which meant that this thing was very lightly loaded. I mean, if I had a little area like that that held this whole shaft together. Now, sure, it's on the outer radius, and we all know that the moment of inertia goes as r to the fourth of a cylinder, but even so, that's not a very big area. And you had to have a big defect. That little defect right there wouldn't have been a problem. In fact, Navy, or submarine propeller shaft is hollow, because you don't need that, and that's a bunch of extra weight, so they go to the expense of machining it out. Well, you can't do that for a low-cost surface ship. I mean, this thing only costs a couple $100 million, right? So you can't afford that to hollow it out. And that defect wouldn't have been the problem. It was the clink, the brittle fracture that occurred during heat treatment that did this in. And you can go through and you can calculate the types of stresses in the furnace. You have to assume what the emissivity, because it's mostly radiation heat transfer, but we did all that. And you can show that you can get, in a time of putting that in the furnace, after about 1 hour, you can get 100 KSI residual stresses in that thing on in the center. So that's sufficient to, even in these types of steels, to cause the thing to fracture. Now, the more interesting thing about that was, why didn't they find it? I mean, we do a quality control inspection, and we're going to talk about different quality control things later. You can do ultrasonics, and we'll talk about ultrasonics later, but basically you have an ultrasonic transducer, and you put ultrasound in, and if there is a flaw, then you'll get a reflection, and you look on your oscilloscope trace on a good piece of material, all you get is the back wall reflection when it goes all the way through and back. Here, you have a flaw in between, and so you'll get an intermediate peak, which tells you got a flaw. And this thing was supposed to be ultrasonic inspected. It was actually going to be inspected at the shipyard, but they decided, I mean, first it was supposed to be inspected at the steel plant. In fact, it was. I'll tell you the story there. So here's an actual trace showing the oscilloscope, just another thing of the same type of thing we saw before. Turns out that it was supposed to be inspected at the shipyard, or at the steel plant, and then sent to the shipyard, and the shipyard was going to do incoming inspection. And then, in order to save some money at the shipyard, they decided, well, it's already been inspected at the steel plant. This was, they decided, well, that's redundant. We don't need, we can rely on the steel company inspection. Well, the problem was, there actually is a sheet at the steel plant in their records that showed that the ultrasonic technician found this football-shaped defect. In fact, he's got a little drawing of it on the sheet. It shows this kind of 12-inch by 8-inch thing. I mean, he sized it with his ultrasonics. And what happened is he went in to tell his boss that he had found a flaw. But they had already scrapped 2 of these shafts. And they were only making 8. They were making 6 for the ships and 2 spares for the fleet. And they had already scrapped 2 of them. And they were losing their shirts on this job. They really shouldn't have bid it because they didn't really have the capacity at the steel plant. But they were losing their shirts on it. And the manager threw him out of his office and said, I don't want to hear about it. So the guy, being a good little soldier, just wrote it up and filed it away. So it's not as if people didn't know there was a flaw there. They just didn't bother to report it because you shoot the messenger, right? And the shipyard, trying to save a little bit of money, which actually is not necessarily a bad thing, said, why should we do redundant inspection? We shouldn't have to check on our suppliers. They've got good suppliers. They're ethical. They're reputable. They'll do all the right things, right? And most of the times they do. And in this case, nobody got hurt. It only cost $10 million, so it was no big deal. But sometimes people do get hurt when those types of things happen. But it turns out usually when you have a failure like that, it's because someone did cut corners or someone did fail to do things. The real problem here is, yeah, they should have found it. It was a human error, really. It was really the person who should go to jail on this, if anyone had gotten killed, is the manager who refused to listen to the report and told the guy he didn't want to hear it. But I can think of things in my own, right here at MIT, on a promotion case once upon a time. Tried to tell the department head there was a problem, and he told us he didn't want to hear it. And 3 years later, it blew up and cost MIT, I mean, it just didn't blow up, no one got hurt, but it blew up figuratively, and MIT ended up paying a $750 million settlement, okay? Because again, a manager who doesn't want to hear the bad news and doesn't want to have to report it up the chain, right? So that's what happens. It happens in all kinds of organizations. And it's not because we don't know how to make things properly. It's because we choose not to a certain extent. Anyway, so that's the story on that. These forgings. Why do I go to hipping and forging and things like, or trying to get in near net shape? The Air Force 20 years ago started a project on near net shape fabrication. And the reason is, if you actually look at how much material you buy of metal, how many pounds of metal you buy to make some aircraft engine part, some simple little turbine disc part, versus how much you actually fly. They call this the buy to fly ratio. Okay? Typically for a forging like that forging that's in the back of the room that I showed you before, the buy to fly ratio, after they've done all the machining and everything, might be 30 to 1. You buy 30 pounds of material for every pound you actually fly. And the other 97% of the product is machining chips. Now this is very good if you're in the machining business. Okay? It's not so good if you're paying for the people to do the machining. And it's also not so good when you start thinking about the fact that in these nickel-based superalloys, you may be paying $20 to $30 a pound for the original material. So if you're paying $30 a pound, for every pound of material you fly, you paid $1,000. Now you can get some scrap value back when you remelt those machining chips, but you paid $1,000 for good solid material to fly 1 pound of material. And that's why, you know, the cost was going horrendous. With hot isostatic pressing, you can get to buy to fly ratios in the 5 to 10 regime versus 30. In some cases, with other types of things they call isothermal forging, they basically don't just kind of slam the thing with a hammer. They actually come down with a very expensive die and they just slowly forge the thing. It may take an hour to forge it. Okay, but they hold the part at temperature and the dies are hot, obviously. So the dies have to be made out of very good material, very high temperature material, and they basically can end up with something that may be a 2 or 3 to 1 buy to fly ratio for some of these things. So one of the major problems of complex parts that have to be light, like aircraft parts, is this buy to fly ratio. And the Air Force has gone from, I think, 25 years ago, for all the forgings they bought, they used to be at a 30 to 1. I mean, some of them were 100 to 1, and some of them were only 10 to 1, but they averaged about 30 to 1. I think they're down below 10 to 1 right now, but I don't think they're below 5 to 1 in terms of pounds purchased versus pounds actually used in the final component. And the rest of it is just machining chips. And given the fact that machining costs something too, just for, you know, not just the cost of the material, but it costs something to machine a pound of material too. And if I have to machine away 29 pounds, that costs quite a bit. So that's why they go to things like hot isostatic presses that can that may cost $100 million for the facility, or a couple $100 million, and cost $1,000 an hour to run, because there's some big savings, but only in very specialized parts. Okay, any questions on any of that stuff? Now I want to start getting back into, I'm going to start talking a little bit about steel, but I want to, welding of steel, welding of different materials. But I want to talk a little bit about rolling first. I mentioned that the main thing, the thing that every metallurgist would like to do is get finer grain size, smaller grains in the product. In fact, that little piece of copper back there that we passed around once before, that has very large grains. It turns out that's got about 0.1% silver in that particular alloy, which makes it more resistant to grain growth, although not in the straight cast form. But it turns out the competitor's product, which was much better, you could not see the grains with your eye. You'd have to go to a microscope. They're so small. They're on the order of about 20 microns in size, or about a thousandth of an inch in size. A pixel on the computer is, or on, well, let's say not a pixel, but if you take a laser print, 300 dots per inch, that's 3 thousandths of an inch. At 1200 dots per inch resolution, that's 20 microns, which is about the grain size of the really good copper alloy they ended up using for Amtrak. And the way they get that is by what they call controlled rolling. They didn't do exactly controlled rolling in the bar, but what they do for steels, this is a phase diagram where you plot temperature versus percent carbon in steel. All steel is an alloy of iron and carbon. That's the definition of steel. And typically it's less than about 2% carbon. So 2% carbon would be over here. Your cast irons are greater than 2% carbon. Most of your steels are less than 1% carbon. This is 0.8% carbon. This is face-centered cubic steel, the non-magnetic form. This is body-centered cubic steel, actually right over here. And this is actually a mixture of the two. This is also a mixture of FCC and BCC, which are the crystal structures, face-centered cubic and body-centered cubic. Well, you change the crystal structure here, the arrangement of the atoms, when you go above this temperature, which happens to be 723 degrees centigrade. This temperature is 910 degrees centigrade. Any steel metaller just has all this stuff memorized. I can remember one of my students who had been a mechanical engineer at another university was in his first thermodynamics class, first couple of weeks, and a professor who's since passed away, but a very world-renowned thermodynamicist who had grown up in the steel industry, put up that diagram, that's only part of the diagram, on the board, but he didn't label the axes. And my student raises his hand and says, Professor, what are the axes there? He looks up and says, you don't know the iron-carbon phase diagram? Who's your advisor? That's what he said. So, of course, my student told him who his advisor was. But there's no reason why you have to know, because that professor is dead, okay? You don't have to know the iron-carbon phase diagram, but the point is, iron and titanium as well, and a number of metals, actually transform the crystal structure in the solid state. The melting point of steel is way up here at 1600, or actually 1536 degrees centigrade, okay? I haven't drawn the rest of that diagram. I haven't drawn the cast iron part of the diagram. But if I cycle between these crystal structures and allow the material to change and form new grains, and I do it the right way, and I also deform the steel at the same time, and I cool it down when I'm all done more rapidly than just letting it air cool, I can end up with very, very fine grain size. I can end up with grain sizes that are, the grain volume is 1,000 times less than it would be for typical old steel that you would build a building out of. And that steel can have double the strength and 5 times the toughness of the type of I-beams that you usually build a building out of. It's called controlled rolling, or, well, it goes by different names. It was originally called controlled rolling because what I do, in the old days, if I went back to the 1950s and 60s, I would roll at high temperatures up here where the material is nice and soft, and I didn't have to have a lot of power in my presses. In the oil exploration and stuff, they started, the Italians ended up building one of the biggest presses and rolling mills in the world, down in the boot, in the heel of Italy, okay? Because it was a good place to ship this stuff around the world from there. They had enough power in their rolling mill, they could roll and deform the plate at temperatures down as low as this, because the steel is starting to get stronger down here, okay? You don't want to roll down here, but you really want to roll in this, what we call two-phase region, because you can get these very fine grain sizes. That was called control rolling. It actually was developed for sheet material in the United States in the 60s, but of course, the American steel industry was not using the technology they had. They were waiting to get beat by everybody else in the world. Then the Japanese in the 1980s came up with accelerated cooling. Accelerated cooling may or may not make use of deformation up here, but rather than just letting the stuff cool down in the air, they actually built whole lines where they would spray water on the plate to cool it down more quickly. Now, you don't hose it down, you have to kind of have a nice uniform stream, and you have to be very careful because if you don't do it properly, you end up with a pretzel rather than a flat plate. Because you're going to cool the steel more quickly on the surface, you're going to have tremendous residual stresses. And so in the early 80s, the Japanese started doing this. They were getting very good grain size, fantastic grain size. And with that, you can use less carbon. You can go lower and lower. You can go further and further over here. And why do you want to be over here at around 0.1% carbon or less? Because it has excellent weldability, no cracks. Okay, and so you were able to make steel that you could probably save $200, $300, $400 a ton, which is the price of the steel, almost, or half the price of the steel. You could save that much money in the welding cost. You didn't need to preheat the steel. You didn't have to do anything fancy. In fact, if you wanted to crack the steel, you couldn't do it. The stuff was so good, because they ended up with this fine grain size and low carbon content. Okay, so that's called, now we call that thermomechanical controlled processing. So you're doing both mechanical working of the steel, rolling at different temperatures. You're doing accelerated cooling, so there's the thermal part of it, and it's a controlled process of the steel to get very fine grain size, very low carbon, and some of the steels that you produce by this now have very good grains, very good strength, very high weldability, and just save a lot of money. HSLA 65, which the Navy wants to implement for the Nimitz hull, is basically a TMCP steel. It wasn't until about 1990, there's a Title III program where the government basically comes in and helps the company pay for the processing facilities, but then they have the right, the government has the right to make things. The government the Navy put in a Title III program, I think at Lucan Steel. Basically built them what the Japanese have been using for 10 years already. When I spent a year with the Office of Naval Research in Tokyo, a lot of what I was doing in the mid-'80s was learning about what they were doing. Now the problem is, if you don't cool this thing just right, everything warps and distorts. Well, they got rid of that, and you actually can also get rid of that by just straightening and flattening the stuff. But the problem is, when you then go to try to flame cut the stuff into a complex shape that you're then going to bend, it turns into a pretzel. Because you may flatten it so it looks okay. I remember going to Korea in 1985, visiting one of the shipyards there, and the Koreans had built their own steel company, and the government actually helped them build the steel company. It's partly government owned. And the shipyards in Korea were doing 18% of the world's tonnage of commercial ships, and they were starting to get into the offshore platform business. And they really, in order to compete in the offshore platform business against the Japanese, they really needed to use TMCP treated steels. In 1985, the Koreans didn't have those types of facilities at the steel plants, and so they got an exemption from their government to be able to buy the Japanese steel. Because it was so much more productive, that was the only way they could compete with the Japanese shipyards at that time. Now, since then, the Koreans have their own and stuff. But with the Koreans, and they told me that the only thing they could use this because all you're doing is forming it very simply. They couldn't make complex shape of a hull, because if they tried to do that, they tried to flame cut out the shapes, everything turned into a pretzel. And they said, why is that? Or what's going on? I said, well, it's because same type of thing as we talked about tempering of glass and stuff. If I cool the stuff off, I can end up with, as it's coming down from temperature, I can end up at the end with compressive residual stresses and tensile center stresses. But if I then cut that, I relieve some of those stresses, and the whole thing, I've got residual stresses in that plate. And all of a sudden, when they started asking me that, I realized that I had seen things when I visited the Japanese shipyards where they were doing some really weird things. And I'd ask them about it, and they kind of passed me off, okay? They wouldn't give me a straight answer on it. And, to be polite, I wouldn't say, I'm telling you the real truth. Because why should they tell me the real truth? They had technology, and they didn't necessarily want to give it to me. But for example, one of the things they were doing is, here's a plate, and let's say I'm going through the panel line, and I see them, they have their computer-controlled machine. It's basically running this cutting torch to cut something out like this. Or actually, even simpler, they were going through the plate, and they were cutting off like 3 inches off the side of the plate. Well, why didn't you just buy it from the steel mill, right, to the right width. But they weren't just doing that. They had a torch right here, and then right, oh, I'm sorry. They had a torch that was cutting its size, and then, no, that's right. Then 3 inches beside that, they had another torch cutting 6 inches behind it, cutting another couple inches off. I said, well, why are you doing a double cut? Why don't you just cut it to the width you want it with one torch, which is what you do anywhere else? Oh, no, it was just quality. What do you mean quality? I didn't say that, but that's what I was thinking, okay? I mean, you're only going to end up with the final cut, you know, you're cutting off the other cut. So, but it meant, yeah, it was quality. Actually, it was a truthful answer, because you get a heat pattern from this cut, and I'm still in the heat affected zone. There's still temperature when I make this cut. And what they were doing is they were balancing the stresses and compensating so they wouldn't turn it into a pretzel. Now this is all empirical type stuff. They had to learn how to cut this stuff. There's a whole technology to being able to even flame cut this type of steel. Okay. Another time is when I saw one torch here and another one. Oh, I saw one torch preheating ahead of the flame cut, which you don't need to do. But again, they were changing the thermal stress pattern so that they actually did their flame cut. They had compensated or relieved these residual stresses so the whole plate. And so actually a year ago when I was working through the American Bureau of Shipping on this HSLA 65 thing, that was one of the things I told the Navy, that, you know, when you start to use HSLA 65, you're going to find that you need to learn what the right type of flame cutting technology is in the panel line, or otherwise you're going to have all kinds of distortion. It's going to cost you a fortune. It took the Japanese 3 or 4 years in the early 1980s in their shipyards to work it out. I was seeing the results in 1984 and 85. The Koreans had just started using the material, and the Japanese steel companies would not tell the Koreans how to solve the problem. They knew. They had worked it out with the Japanese shipyards. But if they gave the technology that they had developed to the Korean shipyards, then the Koreans would be able to compete with the Japanese shipyards. And so it's, you know, just taking care of your own economy type of thing. So those are some of the things that you have to worry about. I mentioned before on the chaparral steel stuff, I showed you a picture of their controlled rolling, or actually not controlled rolling, but their rolling of dog boat shape for I-beams. Okay, this is a continuous caster. The stuff has been turned sideways. It started up here, way up here, 2 stories above, and they're casting in I-beam shape. This is the cut back here. You can still see the stuff is hot coming out of the caster. And they've got an oxygen lamps here. You don't even need the acetylene here. You just blow pure oxygen on it because the steel's already hot. And you just, pure oxygen just cut right through the hot steel. Okay? So you just have an oxygen lance that cuts it off. And the lance is moving at the same rate as the strip, so you get a nice straight cut. Not really, you know, super technology. So now you end up with, instead of a rectangular piece of what we call a billet coming from an ingot, they actually cast something that's already almost in the final shape of the final I-beam they want. Instead of 28 passes when you're starting out with a rectangle, it only takes 9 to 11 passes to end up with the final I-beam. Not only that, they can roll thinner gauge I-beam than if you start out with a rectangle. Why? Well, 28 passes, the steel's got a lot of time to cool. 9 to 11 passes, the steel stays hot, which means you can roll it down thinner. So they can now make I-beams that are only like 6 pounds per foot. I mean, they sell I-beams at kind of pounds per foot. A big heavy I-beam might be a couple 100 pounds per foot. A smaller I-beam might be 50 pounds a foot or 40 pounds a foot. Chaparral steel can make 6 pounds per foot I-beams. Now you can make motorhomes out of rolled I-beams. Okay? Now you're getting light enough in your steel gauge structure. But in addition, you got a smaller solidification zone. It turns out the structure here, you don't end up with this bad columnar structure. You end up with what we call the equiax structure. You saw the columnar structure in the piece of copper. You also saw the very fine grain, the more fine grained structure. The whole thing is that finer grained structure. And so now remember, you get finer grain size because you're cooling more quickly. You get finer grain size, you get more strength and more toughness. Turns out if you go, I don't know if I mentioned this before, if you go to the American Institute of Steel Construction, civil engineer specs, for building buildings, they have 3 grades of steel, 36 KSI, 50 KSI, and now a few years ago they added 70 KSI steel. Why? Because we're pushing up the strength of steel with the same weldability because of accelerated cooling and controlled rolling. It turns out Chaparral only rolls one type of steel. It turns out with this continuous casting technology, they get 50 KSI strength with 36 KSI steel weldability. And so you order 36 KSI, they ship you the steel. You order 50 KSI, they ship you the same steel. It's different prices, okay? But it's certified to a different ASTM spec. It used to be they had to make 2 different types of steel and inventory 2 different types of steel in their yard. Now they only have to inventory 1. Because they can't even make 36 steel as lousy as 36 KSI anymore, okay? And it used to be, when you went to 50 KSI, you were paying a penalty in toughness. Now you're getting both toughness and strength at the cost of the old cheap stuff. Okay? So there really is an improvement in steelmaking technology. And some of these things, even though it's an old, stodgy industry and no one can make money in it and things like that, there are still some exciting things going on. Now to finish up, one thing I ought to do, and we'll talk about welding of steel next time and welding of aluminum. Just to remind you, first of all, don't tell the safety office I'm lighting propane torches in classrooms. But, you know, you can, I don't burn my finger, right? So after class, if anyone wants to come up, you can smell a little something here. But, yeah, I haven't burned my hand, okay? Just to prove it works. Do it more than just